Hi everyone. Welcome to this session with a title called AI-Aware for Code Generation and Beyond. My name is Lingming Zhang. I'm a professor from York University in Canada. So the first speaker is Dr. Lingming Zhang, who is an associate professor in the Department of Computer Science at UIUC. His main research interest lies in software engineering and programming language, as well as the synergy with machine learning. The goal of his research is to improve developer productivity and software quality. He's a recipient for a number of awards, including ACM SIGSOFT Early Career Research Award, NSF Career Award, UIUC Dean's Award for Excellence in Research. In addition, he's also the recipient for multiple Best Paper Award. He worked with a number of different companies, such as Alibaba, Amazon, Google, and Kawaii, Meta, NVIDIA, and Samsung. So he currently serves as program chair for ASC 2025, LLM for Code 2024, and associate chair for UPSLA 2024. So today he's going to talk about towards Crystal Clear LLMs, StarCoder2 and Magicoder. Please.
Okay, great. Hello, can you hear me? Okay, great. Thank you, Jack, for the very nice introduction. So today I'm very happy to be here to present our recent work on towards crystal clear code language models. So I'm going to introduce two of our recent work, StarCoder2 and Magicoder. Okay, and so first, what are language models? So basically, they're just models that assign probabilities for token sequences, and they are typically built on the transformer architecture with attention, right? So to have some very simple example, suppose I'm going to generate this element, print variable +1. So everything is about probabilistic computation, right? So just about the probability for producing the first token, and then producing the next one based on the first one, and then produce the last one based on the first two, right? So it's all about probability computation. And then when we produce the last token, for example, we can assign more weights to variable y because we are summing up one and variable, so they have to have compatible type, right? So that's why those models, they are able to capture such subtle relations. So, and the overall idea is not that new, right? It's basically even the old n-gram model has such a kind of idea. But why the large language models are so powerful nowadays, right? So, simple reasons. For example, first, they have huge number of model parameters, right? So for example, this is a plot about some representative models in the past few years. You can see that starting from transformer, which is a tiny model now, right? Now we are having models with over 1 trillion parameters, right? So I put Jensen's headshot there because Jensen just confirmed on the NVIDIA GTC day that actually GPT-4 has over 1 trillion parameters, right? So we have huge, larger and larger models nowadays, and they can really compress a lot of information, right? And where do we get those information? So they can be obtained during the pre-training phase. For example, a large amount of unsupervised data can be used for pre-training those large language models. So they can be from, say, Wikipedia, like an online discussion, right? It can also be from GitHub. So when it comes from GitHub, it includes a lot of code information, right? Because of that, a lot of the recent large language models, they can really perform competitive programming, right? So they can have show very impressive performance in coding tasks. And so what are the current popular code language models, or the models that can perform programming tasks, right? So we have a lot of like open source ones and also closed source ones, like OpenAI, like GPT, like series, Gemini, Cloud 3, DeepSeek, Mistral, and so on, right? So, and they have shown impressive results. For example, GitHub Copilot, which was built initially based on Codex, but now based on GPT-4. So they have already got over 1 billion users all over the world, right? So people are using that in their every daily development to build faster code, right? So, and it has been reported that over 40% of the programs written by those developers can be automatically generated. So which is quite impressive, right? And but what's the current status for those code models? So you can see that actually some of those are closed source models, some of those are like open source models, but what did they open, right? So for example, even the open source models like DeepSeek, Mistral, Gamma, and Llama, so you can only have the model weights, you can only access the model weights, while the actual data used to train those models are still not available, right? So the only one I know is StarCoder, for example, which release both the model weights and the actual training data. So, but of course, like StarCoder is a little bit outdated now. So, Here's the issue. So there is a lack of fully open source and powerful code language models. This is very, very important. The reason is that if you don't have such fully open source code models, it can hinder model replication, enhancement, interpretation, decombination, a lot of things, right? Because we don't know what's going on. We don't know how they were trained even, right? This is a big issue for the community, for the entire community. So, and also most of the models, we mainly focus on mainstream languages. For example, many of the very, very popular open source code models like called Llama, DeepSeek, they are just pre-trained on any language, like basically the most popular ones, right? So how about those like emoji languages, low resource languages, right? So they are not well handled. Okay? And they also mainly focus on source code level. They mainly focus on the source code completion tasks, right? Because they're pre-trained on source code information. So, and of course, they have limited cross-file dependencies because in the pre-training of the code language models, they typically mixed code files from different projects altogether. So the models are not pre-trained to understand the cross-file dependencies well. So there are, of course, a lot of other issues, right? So, but that's the current status of the code models. Although they have achieved impressive performance, there are still a long way to go for fully transparent, like powerful models, right? So, and this is what we have been exploring in the past few years. So today I'm going to introduce some of our own work, right? So this is the basic agenda. So I'm going to first talk about StackV2, which is the most extensive code provisioning corpus. So, and on top of that, so as part of the big code team, so basically we together trained the StarCoder2 model based on the StackV2 data, so which is a series of fully open source base code models. And of course, our StackV2 data can also be used to pre-train any other code models, right? And even on top of that, we also built Magicoder, which is a series of fully open source instruction-tuned code models. So this is the basic agenda for today's talk. So let's get started with the first part, which is the StackV2 and StarCoder2. Okay. So this is the StackV2. So how do we collect the data for StackV2, right? For pre-training StarCoder. So this is the basic process, how we select data. So we start with the software heritage project, which is an awesome project with including source code from all the GitHub projects. So initially we have over 2 million code files, only 200 million projects, including 18 billion code files. And then we go through a long list of checks, right? First, we check if the licenses are permissive, right? And we further do some deduplication. So it turns out that we can have over 32 trillion bytes after deduplication, right? And later on, we also remove all the personal identifiable information, emails, names, all those information. And then later on, we also perform some scanning using some static analysis tools to remove potential malware, right? And we further, because there are also organizations or users, they don't want their code to be included in your pre-training dataset, right? So we also provide an opt-out process. So users and organizations, they can choose to request that their code to be excluded from our dataset. So it turned out that there are over 1,000 repositories and 91 users, and also 22,000 files were excluded from the dataset. So, and after that, we have the final dataset, and then actually we create two subsets, one with 500 billion tokens and 17 languages, which we use to train StarCoder2, 3B and 7B versions, and we have another one which is with over 700 billion tokens, and we use that to train the StarCoder2 15B version. It includes over 600 languages. So that's the basic overview of the StarCoder2 project. And so I'm just give you some brief introduction. How do we prepare the source code for all those projects, right? So as I said that initially, not only StarCoder1, but also many of the other code language models, they basically just mix code files from different projects all together to train the model. Basically, every single file is kind of embedded by itself. For example, for every code file, I guess you can see my mouse, right? So basically, this is one file, the representation for one file during pre-training phase. You can see that you have the repository name, file name, and also the code information. That's it, because you encode every single file in isolation. And during the pre-training, you have to mix files from different projects all together. Okay? So in this way, it is very hard to capture the cross-file dependencies. So to give you an example, say if you're going to perform next token prediction, so which is the most popular training objective for code language models. Say if you're going to predict this token, this gray area is the next token you want to predict, right? And of course, you rely on earlier tokens, say from the same file, file 3, right? But you can see that we are like putting files from different projects together, right? So it is very unlikely this token going to depend on earlier files. So a lot of connections are missing for long context dependencies. Okay? And because of that, in StarCoder2, actually we have a revolutionary design. So what we did is that we group all the files from the same project all together. So this is basically how we did it. So basically you can see that this is the repository name, right? And then we have a file separator, right? And then we can have file path 1 with the code for this particular file, right? And then we have another file path 2 for code in the other file, right? Basically, all the code files within the same project, they are grouped under one repo kind of tag. So in this way, the models, they can be pre-trained to learn the cross dependencies across different files from same project because they are joined together during the pre-training phase. So in this way, we can effectively capture the cross-file dependencies for long code generation, long code understanding. That's why we can generate a lot of like long realistic programs based on simple prompts. So again, illustration, you can see that now all the files within the context, so they are from the same repository 1, for example. And you can see that when I predict the next token from file 3, I will have a lot of dependencies, right, on earlier files because they are from the same project. Very likely I'm going to invoke methods from other files, right? So a lot of dependencies will be captured based on this like neat design. And after that, actually, that's all about GitHub code, right? Besides, beyond GitHub code, we also feed a lot of extra information to train StarCoder2. So which includes like say like pull requests, issues, Jupyter notebooks, Kaggle notebooks, documentation, Wikipedia, Stack Overflow, archive papers, and even intermediate representations in terms of LLM. So those numbers are in terms of the billion tokens. So this is all the data we have for, besides the code information we had from the Stack V2. And due to the time limit, I'm just going to give you 2 examples about the 2 sources of data we have. For example, this is a very new kind of a data set we had. This is a data set for LLM IR. Basically, as I said, all the previous tools, they are mainly pre-trained based on source code, right? But there are a lot of tasks which require the models to have a deep understanding about the program semantics. They need to understand different representations, right? So because of that, actually in this project, we also feed a lot of IR information, intermediate representation information to the model with the hope that the model can learn even like more in-depth information about the code, about the semantics. So what we did is that we collected over 4 million self-contained compilation units from accepted solutions like to programming problems, and then we form those kind of pairs, source code to like LLM pairs in these 2 different ways, like source code to IR to source code, each with 50% probability. And then how do we get that information, like this huge chunk of information? So what we did is that taking source code from a lot of different languages, from C to even to Fortran, even NIM, right? So, and for different languages, we compile that into using different compilers. In this way, we can obtain the unified LLM IR for multiple languages. And all those information will be fed into the model with the hope that the model can learn those kind of latent, like intermediate representation information. So that is the basic idea for this extra data set beyond source code, right? And another information I'd like to give an example is about documentation, right? So which only includes like 1.6 billion tokens, right? We include all those sources. For example, for this particular documentation, like code documentation category, we include like all the documentations from all the projects from over 10 package manager platforms, including Python package index, Bower, like Conda, like NPM, Julia, and so on. We also include over 20 like documentation websites for very popular projects like Linux and TensorFlow, and for very popular languages like Java and C#. Right? And also, we have even included the PDF version for over 3,000 like programming books from the free programming books websites. So with the hope that the model can better understand the basic concepts about programming. So this is all the information we had for this category. And based on all those information, including GitHub code and all those dimensions with different information, we can now pre-train the StarCoder2 project, like a model. So basically, you can see that it is a typical decoder-only architecture. So we did have some modifications. We added rope support, we added group query attention, we added like flash attention too for faster inference, faster training, right? And also, we train the model on two basic objectives. One is next token prediction, right, which is pretty common. But next one, we also train the model to perform fill-in-the-middle tasks. So in this way, the model can also learn how to perform in-filling tasks, which is very important for realistic code completion. And in total, we have trained 3 models in this series, right? 3B, 7B, 15B ones. And these are the token numbers and also GPU hours they consumed. For example, you can see that, for example, StarCoder2, 7B one already consumed over 100,000 GPU hours using H100. It's pretty high-end GPU already, right? And so we use cluster services. We use over 1,000 GPUs from ServiceNow, Hugging Face, and NVIDIA. Of course, this is a big project in collaboration with the big code team, right? So it does involve resources from those organizations. And here is the brief summary about the results. So basically, this is a result we had. So for example, for every figure, we have included different tasks, including code completion, code reasoning, data science task, math, and even repository level code completion. So you can see that, for example, for the 15B version, so across all the models, all the existing open source models of similar sizes, we can achieve the best performance in almost all the different tasks, right? So we are only slightly worse on the code completion, but we are the best on all the other tasks. And even compare against the much larger model, say, when we compare StarCoder2, 15B with some over 30B versions, 30B models, DeepSeek-Coder, 33B, CodeLlama 34B, we also achieve close or even better performance on some tasks. Okay. So to summarize, StarCoder2 is a series of fully open source based code models. They are crystal clear, so you can obtain everything from the model, from pre-training data set to everything. Okay? And they achieve state-of-the-art performance now on a number of different coding tasks. So I highly encourage you to try it out if you're interested. We also released the pre-training dataset, which is Stack V2. We have we have covered over 600 languages, over 30 trillion bytes data after duplication, right? So this is a number of stars and downloads we have already got. Okay, try that out if you're interested. And okay, so basically, this is the last part. I just go quickly with this. So we also, StarCoder2 is the best model, right? We can also perform instruction tuning on those models. So we are going to also propose Magicoder2, which is fully open source instruction tuning for code. Basically, the basic idea is very simple. So this is an instruction tuning. I'll go very fast with it. So basically, what it does is that if you have a best model, they may not work well if you have prompt answer, right? They may not work that well. But if you can provide a lot of instruction response pairs, use that to further fine-tune the model can perform much better. So if you fine-tune them, you can get an instruct model, and you can get much better results. So if you have a prompt, then you can answer this question very well. Okay? And of course, there are a lot of existing techniques, but they have some issues. There's existing techniques called self-instruct. They just try to generate instruction data based on similar ones. There's another one called evil instruct, which is widely used for instruction tuning of code, and they just basically try to evolve the existing instruction data into more ones based on some adding more constraints, adding more reasoning steps, and so on, right? But they all have system bias because the models they will only dump the most frequent information. Okay, and on top of that, we have the Magicoder idea. So we can get inspired from open source, for example, Stack. So what do we do? So the idea is extremely simple. So what we did was that basically we have the open source code snippets, right? So we can randomly get open source code snippets, and we use that as reference here to guide the model to create different problems. So in this way, the problems are diverse, and they are realistic, right? And also they are controllable, okay? So, and this is the result. Basically, with this very simple idea and fully open source dataset, we can achieve even better performance than Gemini and GPT 3.5. So based on some very simple open source models. And so summary, so a novel instruction tuning method from open source as serious new models, we can beat ChatGPT 3.5 using our 7B model. Okay, we already got a lot of stars, a lot of downloads on GitHub and Hugging Face. Try that out. You can search Magicoder if you're interested. And a lot of companies are already adopting our methodology or dataset for training their own models. Okay, with that, I think that is my last slide. Thank you so much. Yep.
So, thanks, Lingming, for the talk. So same as the sessions in the morning, we're going to have all the questioning in the end during the discussion period.